Hello, I am Vidushi Goyal from University of Michigan, and I will be presenting my work Seesaw, End-to-End Dynamic Sensing for IoT using machine learning. I'm a PhD candidate in CSE at UMich. I work in computer architecture to optimize edge devices and applications. IoT devices are growing exponentially and are present in all aspects of life, ranging from medicine, precision agriculture to entertainment. However, small form factor and limited accessibility for battery replacement makes them energy constrained. Upcoming edge devices host multiple sensors, provide enhanced user experience. This leads to a wide diversity in power distribution, with only few power-hungry sensors consuming major fraction of power. We leverage this diversity in power profiles and propose Seesaw, an end-to-end dynamic sensing solution, reducing energy consumption from sensing at edge until data transmission to cloud. Seesaw uses lightweight sensors to govern the sensing or sampling rate, power-intensive sensors with minimal impact on accuracy. To achieve this, we deploy a low overhead prediction mechanism which can be supported by tiny microcontrollers. We use lightweight decision tree predictors which are trained for user-defined error tolerance. The robustness of these decision trees determine if the correlation learned between the low sensors and power-intensive sensors are valid or not. If valid, these decision trees predict the optimal sensing rate of power-intensive sensors at runtime. The nodes of the decision trees represent the sampling rate, which increases down the tree. If the application supports runtime error tracking, we move the start node dynamically to restrict error. The start node traverses down the tree as error increases and vice versa. The first use case for which we show benefits of Seesaw is mountable camera like a GoPro. Here, the speedometer present in GoPro for user information is used to guide the frame rate of camera. Faster moving videos need higher frame rates to capture all motion, whereas slow videos have a lot of redundant frame and can drop frames to move to sleep mode and thus work with lower frame rate, as shown in figure. In the schematic here, we show speedometer along with motion vectors, where motion vector take care of scenarios when camera is still and surroundings are moving. Together guide the frame rate using a decision tree predictor trained for different error tolerance. My second use case is fitness tracker like a Fitbit. Here, Seesaw finds that compass heading, which are indication of presence of twists and turns the track, can guide the GPS update rate. For straight tracks, GPS update rate can be reduced, whereas for tracks with more turns need frequent GPS location update. In the schematic, we showed that the compass headings from the IMU sensor guide the GPS update rate. Moreover, due to the feasibility of real-time error tracking mechanism, where error is difference between distance calculated from pedometer and the GPS, we use our feedback mechanism to dynamically change the start node of a decision tree predictor to restrict error. For experiments, we use evaluation board setups, which tries to replicate the user device. For mountable camera, we train decision tree for 3 error tolerance, 5, 10, and 20%. Error is determined by VMF metric given by Netflix, which has 3 components. VLM and VIF compare image quality, and Pixel Motion compare the interframe motion difference between 2 videos. Our frame rate ranged from 30 frames per second to 20. We also conduct a user study to correlate the quantitative VMF error with human perception. We show that battery life for various error tolerance limit increases as compared to baseline, and the battery life improves from 2.5 hours to 4 hours for 20% error model. On the left, we are showing the VMF error across videos for a different error tolerance model, then we see that the average error is within the set limit. To the right, I show more interesting results from the user study, where we ask the user to rate the videos from -10 to +10 as compared to baseline, which is 0, where positive means better than baseline and negative means worse. As shown, the user ratings across different error tolerance are very close to 0, and the users were not able to determine much difference between original and Seesaw. Therefore, it is acceptable.
For example, in this video, I'm showing the original video on the left and the 20% error video on the right. We see as the pixel motion reduces, so does the frame rate and the corresponding power. And the frame rate and corresponding power increases as the pixel motion increases. The overall video quality between original 20% is not much different, with almost negligible difference to the human eye.
Again, for fitness tracker, we trained for 3 error tolerance. We used 100 route GPS routes for training and 100 for testing. The track error is a difference of path integral with the update rate ranging from 1 Hz to 0.1 Hz. Here, the real-time error tracking is possible, which is difference between pedometer distance and GPS distance. We show battery life across error tolerance models and for various activity factor, which represents the fraction of time when GPS is used. For highest activity factor, the battery life improves by 8% for 20% error tolerance model. On the left, the track error across all tracks, and we find the average error is within the set tolerance limit. The plot to the right shows the maximum error to present benefits of error feedback mechanism. With feedback mechanism present, even the maximum error is within set tolerant. In conclusion, we propose Seesaw, an end-to-end technique to dynamically change sensing weight of power-intensive sensor using low power sensor, for which we develop a low overhead decision tree-based prediction mechanism that can be easily deployed on small microcontrollers. Finally, we evaluate for 2 IoT platforms. Thank you for listening, and if you have any questions, contact on the given email ID.